Welcome you all to this discussion on fluid mechanics and machinery. So today we'll be seeing some rules regarding pressure, the Pascal's law, and some problems involving Pascal's law. Okay. So this is actually the syllabus for the unit 1. Okay. So we'll have vapor pressure, capillarity, and also the surface tension. Everything we have discussed in the previous videos, and also we have already learned absolute pressure, gauge pressures. So now we are going to learn the Pascal's law and some application problems. So I'll say what is actually a Pascal's law. So we know very well Pascal's law states that actually the intensity of pressure at a point in a static fluid will be equal in all the directions. Okay. So whatever it is x direction or y direction or z direction, the intensity of pressure will be the same. And in all the directions, in the sense we can say Px is equal to Py is equal to Pz. So you consider the arbitrary fluid element which is of wedge shaped. Okay, so the width of the element can be unity, and we do have three pressures Px, Py, Pz in the directions. So now what happens actually is you can see that there are ABC, angle ABC is theta. The forces acting on the element are, number one is pressure forces which are normal to the surfaces, and also we do have a weight of the element in the vertical direction. So please see that first we are, for equilibrium, all the forces should be equal to 0, right? So first we have sigma x is equal to 0. So we can see what are the forces, Px and Pz cos theta will be equal to 0. And when you consider sigma y is equal to 0, we can consider the weight of the fluid in addition to the Py and also Pz sin theta. So this one we have Pascal's law. So actually we know very well this is a very good example of Pascal's law, isn't it? You take a rubber ball, you will be filling with liquid, and with the help of pen you are making many holes, and we are applying the pressure. What will happen? The water will be coming out from all the holes with equal pressure. That is, the pressure applied at one point of the liquid will be transmitted equally in all the directions. Okay. So another example, this is actually one we are having you can take it as one is ram or one plunger, two models. So one is of this diameter and another is of greater diameter, and the original force is F1 and F2 will be the 10 types of F1. Okay. So actually we can see that the pressure P1 exerted in this area and the pressure P2 exerted in that area will be the same. That is by Pascal's principle, the capital P1 is equal to capital P2. Okay. So the pressure intensity will be the same with respect of the diameters of that ram. So next we are going to solve a simple problem using this Pascal's law. So you are having a hydraulic press. We'll have to read it out. The hydraulic press is having a ram of 30 cm diameter and a plunger is 4.5 cm diameter. So we are going to find the weight lifted by the hydraulic press when the weight of when the force applied by the plunger is 500 Newton. First of all, we have to make clear what are the details available and what we have to find. So first I am writing as the diameter of ram is 30 centimeter and I am taking as 0.3 meter. So diameter of plunger I am taking it as 4.5 centimeter and this will be 0.045 meter. So force on plunger will be 500 Newton, and next we will be finding the area of the ram and also area of the plunger. So now the pressure intensity due to plunger will be divided by, that is force on plunger, that is 500 divided by area of plunger is 0.00159. So we know very well by the means of Pascal's law, the intensity of pressures will be equally transmitted in all the directions. So what happens, the pressure intensity in the ram will be, so we get it as 314465.4 Newton per meter square. So that is what happens actually when you take it as 3,14,465.5 Newton per meter square. In Newton we are having it getting as a larger value, isn't it? Next one. So pressure intensity of ram will be equal to this only. So the pressure, this value is the same. The weight is unknown. So by using the formula we are finding out the value of weight. This is also we get it as a large value. So what we are doing? So we are converting into kilonewton. So we get in terms of 22.2 to kilonewton. That is the answer. So next one I am having a next problem. We are having a hydraulic press of about actually 20 centimeter ram diameter and also a plunger 5 centimeter diameter. So it is used for lifting a weight of 30 kilonewton find the force required on the plunger. Okay, so again I am having diameter of ram is actually a similar problem to the previous one only. Okay, so for the clear understanding, I had another problem. So diameter of ram will be 0.2 meter. So area I am finding out, and diameter of plunger and area of plunger. So weight that is being lifted is 30 kilonewton. Okay, so now what happens again? The pressure intensity divided by the plunger is force by area, and it will be equal to the force acting on the ram will be equal to the pressure intensity in the area of the ram. So we know very well we will have to find out the force acting on the ram when the weight lifted is 30 kilonewton. By using the formula, we have found that the force is equal to 675.2 Newton. This is another problem which had applications of your Pascal's law. Next one. Next, this problem I have done regarding specific gravity. Okay, so that concept also will be included. So I am having an oil of specific gravity of 0.9, and it is contained in a vessel. At a point at the height of oil is 40 meter, we have to find the corresponding height of water at that point. Okay, at a point is what it is actually, we know it as what we have to find the corresponding height of water. So how we are doing? So we know very well the intensity of pressure is equal to density into G into that height. Okay, so that is we take it as rho is actually 900, that is the density of oil, and 9.81 into height. So we know very well specific gravity of corresponding height of water is equal to capital P, intensity of pressure, divided by density of water into acceleration due to gravity. Okay, so we get it as 900, we just replace it, and divided by 1000 is what it is actually, the density of water, multiplied by 9.81, we get it as 36 meter of water. So next problem is actually, I am having it as an open task. Open tank is actually containing water up to a depth of 2 meter, and above it is an oil of specific gravity 0.9 and is of depth of 1 meter. So find the pressure intensity of the interface and also the bottom. So here Z at the interface, we can know that Z1 is 2 meter, and here actually at the height of, at the bottom of the tank, at the height of oil is actually 1 meter, isn't it? Above that, specific gravity of oil we know it as 0.9, and again density of water we already know it as 1000, and density of oil is actually 900. So these values you should know already, these densities. So at interface at point A, what happens here? P, pressure, is equal to density into G into Z. So we know very well at point A what will happen? This height will be 1, isn't it? So now we get it as a value as 0.8829 Newton per centimeter square. At point of B, what will happen? What will be a Z value? It will be at 2. Okay, so this at the bottom at the point B, what will happen actually? So you can see that we have 900 will be actually it will be for your oil, 909.81 into 1000 plus into 1 plus, okay, 1 is the height, isn't it? So 1 is the height, so that is for your oil, plus what is the depth? 1000 is your density of your water into 9.81 into 2 is the weight height of water. So we get it as 2.8449 Newton per centimeter square. Next one, we are having the diameters of small piston and large piston of a hydraulic jack are 3 centimeter and 10 centimeter respectively. Okay, now we are applying a force of 80 Newton is being applied on the small piston. Find the load lifted by the large piston when the pistons are at the same level. Okay, and density of the liquid in the jack is 1000 kilogram per meter square. So what are the details given? Diameter of small piston, area of small piston. So diameter of large piston, area of large piston. Okay, number 1, when the piston are at the same level, what will happen? The pressure intensity of the small piston, we get it as force divided by area. So 80 divided by this area. Okay, similarly pressure intensity of the large piston, we have it as 80 divided by the same. Okay, because the force will be the same. Now therefore the pressure on the large piston will be equal to what values we have got here, that will be calculated as 78.54, that is area of large piston. Okay, so pressure that into area, that pressure is 80 divided by 7.068 divided into 78.54, we get it as 888.96 Newton. Next one. Now the law's previous calculation was when they were at the same level. Now we consider the small piston is 40 centimeter above the large piston. So the pressure intensity of the small piston is equal to 80 divided by 7.068. Now you consider the pressure intensity at section AA. You consider the section, okay, this F by A is equal plus F by A at the section AA, it will be at 40 centimeter pressure density due to height of 40 centimeter of liquid. Okay, so pressure intensity due to 40 centimeter, how it is, rho into G into H. Okay, 1000 into 9.81 into 40, and we are converting in terms of actually centimeter. So only I have divided by 10 power 4. I get the value as 0.3924 Newton per centimeter square. When you take it as for your AA, what will happen? You will have to add that pressure also. Okay, add that also. So I add that pressure. What is this? 80 divided by 7.0868. Okay, that is 1 plus the pressure intensity due to 40 centimeters. So that we are getting as 11.71 Newton per centimeter square. So the pressure intensity transmitted on the large piston will be 11.71 Newton per centimeter square. So force will be, force of large piston is equal to pressure into area of large piston. So that we will be getting as 919.7 Newton. So the next one will be, so we are going to this problem. This is actually regarding the gauge and the absolute pressure. So what are the gauge pressure and absolute pressure at 0.3 meter below the free surface of a liquid, having a density of 1.93 into 10 to the power 3 kilogram per meter cube, and atmospheric pressure is actually 750 mm of mercury. The specific gravity we know very well for mercury. These values you should know already. Is 13.6 and density of water is 1000 kilogram per meter cube. So depth of liquid is 3 meter, and density of liquid we know very well, 1.53 10 power 3 that I have given. Atmospheric pressure head is equal to 750 divided by 1000 is equal to 0.75 meter of mercury. So atmospheric pressure will be always equal to rho into G into Ez. Okay, rho will be the specific gravity of mercury into density of water. Okay, that will be equal to 13.6 into 1000. So we get this pressure atmospheric is equal to 13.6 into 1000 into G 9.81 into 0.75. Okay, that is the atmospheric pressure head. So pressure atmospheric we have it as 100062 Newton per meter square. When you are considering a point which is at a depth of 3 meters from the free surface, we will have to, how will we have to calculate this 1.53? What is it actually? We have get it as 1.53. Next one into 1000 into your well, we get this value is actually density they have given, free surface of a liquid they have density they have given. Okay, that is only 1.53 into 1000. Why have 1000? It is 10 power 3. So that is 1000 to 9.81 into 3. We get the gauge pressure. Okay, now absolute pressure also already we have seen in the section. Gauge pressure will, absolute pressure will be the addition of gauge pressure plus atmospheric pressure. Okay, so we'll get the value answer for absolute pressure. Thank you all for your patient listening, and we shall meet in the next session. Thank you all once again.